So my name is Pat Helland. I work at Salesforce. This is not about Salesforce stuff. I've been doing distributed systems, transactions, databases, implementing them, scalable multiprocessor with Dennis Allison back 27 years ago. I was working with him. But I've been doing this for 40 years. And so, as I said, I'm currently, and I've done work at Tandem Computers, was at Microsoft for many years, at Amazon for a while, and now at Salesforce. And this particular talk is just one of the things that I think about, right? And I called it Mind Your State for Your State of Mind. Basically, the evolutions of computation and storage lead to interesting challenges. And again, these are just my personal observations. I have a whole collection of papers that I write about just random philosophical junk I think of with respect to distributed systems. I actually think in the paper for this, I described it as ruminations, which is this wonderful concept of, thinking this thing over and over again. So this is a paper. It was published just a month ago in Communications of the ACM. And so you're free to go look it up. It's online and it's in hard copy. So I'm going to cover a bunch of things. I'm going to do an introduction. I'm going to talk about what's this state stuff. We always talk about state, we talk about stateless, and no one that I know actually has a cogent explanation of what that is. And let's see if you think this is a way of thinking about it that makes sense. We're going to talk about the evolution of durable state semantics. We'll talk about session state semantics and transactions, something near and dear to my heart because I worked on it for a number of years. Identity, immutability, and scale. Some example application patterns, and then we're going to have a conclusion. So I'm going to start back and talk about the way computing was when I had hair. I honestly had hair at some point in time before I ended up dyeing it transparent. And so I want to look back. Storage has evolved. When I was starting out in this, the only storage you had was directly attached to the one and only one computer you were using. Okay? There eventually came along these shared appliances called a SAN, or a storage area network, which offered some high performance stuff and the ability for multiple computers to whack on some shared storage. Storage clusters contained in the network, which was sort of like a SAN, but a little more loose in the way it was built. And even REST APIs fascinate me. The whole representational state transformation nature of using HTTP in order to make something look like storage, even if it's computation. And so there's this really interesting thing about REST APIs over microservices. Computing has evolved. Back in the day, there was a single process. Oh, maybe 2 or 3 in the same computer if you got lucky, right? And that was called a mainframe region at first, if you were, familiar with IBM stuff. And then you got multiple processes in the same server. I remember how cool it was to start doing RPCs across a little tiny cluster in the same room. That was like a miracle to be able to do that kind of work. Then services and service-oriented architecture. And I did some presentations and talks. I never quite turned it into a paper of what I call a fiefdom, which was an independent, today we would call it a service, and how you would talk across that. And that whole service-oriented architecture and how to do scale with that is a very interesting thing. But that broke apart the transactions that we were familiar with having. We'll talk about that. Now we talk about microservices. And those microservices have little or no state. They come, they go, they're flighty, but they offer some real advantages. Now, computing's use of storage has evolved. We used to have direct file I/O, and we used this thing I call careful replacement for recoverability. We will dig into careful replacement in gory detail, so don't get too stressed if it doesn't make sense yet. But the careful replacement variations are, number 1, because what you're writing might trash the previous value, you should put it somewhere else before you write it where you're going to eventually have it land. That's the first form of careful replacement. And then the second form is that the client can interrupt a sequence of writes, so plan carefully to have a partial sequence by the time you try to do recovery. Those are the 2 things we're going to talk about thematically. Now, transactions came along, and I've been working on transactions, since I was working on databases, but I owned and shipped the stuff for Tandem's nonstop transaction engine. I was working on that from 82 through 91. And how do you build logging and recovery and high performance and making it work? But transactions were implemented careful replacement for the app. They dealt with a bunch of junk underneath in the hardware and the system itself, so the app didn't have to, and made it easy for it.
I think you might have to explain who Tandem was to many people here.
Well, the comment is I should explain who Tandem was. So they were started in '74 and kind of eventually petered out over the late '90s, but I left in 1990. And you would get 2 to 16 computers in one big system. And the actual measured installed base over 4,000 customers, which you can read about in Jim Gray's paper, Why Computers Fail, the measured mean time between failure of the system was 11 years. And there were a number of sites where nobody worked at the company anymore since the system had gone down, because it was designed to handle one of the computers failing and the rest of them continuing on. So I ended up building the logging and recovery part of the database that made the entire system go. So here you are and it was running federal funds transfers and stock exchanges and hospitals and all the things that cared a lot about high reliability would use the Tandem system. And it was transactional, enterprise grade, and highly available was what we were building. And a lot of fun. I learned a lot there over a decade, almost a decade.
Was the OS anything familiar?
The OS was not anything familiar. It was completely separate. The application programming interface was not. And I believe over time it stopped being an important player in the industry, because in the late '70s, if you could buy that piece of hardware, you could afford 50 people with white lab coats to program it, because the software was far cheaper than the big expensive systems of the day, right? And so you could do your customized app. And there were some ISVs that did the apps, but they weren't enough to keep the business going. So as the turnkey software packages came, they didn't run on it. And that's how come you don't hear so much about it anymore. Did that make sense? Okay. But it was actually not that hard to program to, so it was just kind of an unfortunate catch-22 that happened. Okay?
Yeah, the comment I would make was, when I was talking to the Computer History Museum about trying to preserve some of them, they had no concept who Tandem was or why it was significant. And
it kind of happens that way.
Yeah, this is the kind of computer you want your bank account run on.
Oh, it was designed for that, and it succeeded at that, and I'm very proud of the work.
And I had several friends who worked with me, including people I went to college. And at the same time, the California Department of Motor Vehicles got a $65 million Tandem.
I know.
Never got it to work.
They what?
They never got it.
I remember the fight. I do. So let me keep going.
Yeah,
if you don't mind. Okay. Let's talk afterwards. Okay. So implemented careful replacement. Transactions implement that careful replacement, and the SANs implemented careful replacement. But stateful 2-tier and n-tier transactions and doing that came along. Now, and you ended up with key value storage, typically atomic key value. So we see this today. You can do one key's value update in a transaction, but not many of them because of the way they're distributed. And finally, REST put invokes the app code of that resource. Who knows what that does to the affected state when you call with an put with an HTTP with the REST stuff. So there's challenges in modern microservice-based apps. Today, the microservices power many scalable apps. Pools of equivalent services, incoming requests are load balanced. This is a direct image off the PDF for a 2007 paper from Amazon called Dynamo, which I helped work on Dynamo back in the day, and so was part of the initial design. But what you see is the requests coming in, and they're load balanced out, and you do page rendering, and then it comes back, and then they're load balanced out, they do aggregator services, and they come back, and then there's a request routing, and they're load balanced out. And behind it, you see in this picture 4 different stores working to support 4 different service pools. Okay, and so this is the way Amazon was building it, and this way it's still building it. Okay, and the front end part of what you see in e-commerce retail is typically done this way with many different kinds of stores to support many different kinds of pools of microservices. Microservices support many operational needs. They support health-mediated deploy with canaries, rolling upgrades sensitive to fault zones, and fault tolerance. So let's talk about that for a second. The term canary comes back to someone going into a coal mine and taking a little yellow bird with them. Because if there was methane gas and the bird fell over, you got the heck out of the mine. And you lived because you brought that early warning system. When you roll out across 100 different servers, say you have 100 different servers that are working on the same stuff, and you roll it out, that's cool. What you want to do is roll it out to maybe 5 of them and then see what the hell happens, right? And then if that works, then you start keep rolling them out. And that's called canaries. And doing automated canaries. And health mediated deploy is a formal way of saying, I'm going to do it as long as everything's healthy. I'm going to roll out the new version of this thing as long as it's healthy. All of this is facilitated by microservices. Rolling upgrade. I'm going to do my rolling upgrade, but what I don't want to do is I don't want to bring down too many things to kill a fault zone. Or I'm going to count on doing the ones within a fault zone, not a cross fault zone, so I can't handle the failure. And then fault tolerance if things are dying. Things can die while you're rolling out. Durable state is usually not kept in microservices. You go elsewhere to get to that durable state. In this picture here, you see these things right here, which are the services, going down to get the Dynamo instances, or going down to get Amazon S3, or going down to get storage in a backend database. And that's the way you do it. You don't put the state in the microservice because they're flighty and they die, right? You can't effectively update that state across it. If I have 100 microservices, I can't get all of them to know the new state atomically. It's a real interesting challenge you have to. So you push it elsewhere and then versions are cached. Now you have to talk about staleness of cached versions. Sometimes read-through requests to durable state access information that's not in the microservices. Okay, so we're just getting started. That was the introduction. Let's talk about what this state stuff is. Durable state and session state, right? So in durable state, what do you have is stuff that gets remembered across requests and persists across failures. So that's durable state. It persists if something fails. What is it? Database data, file system files, key values, caches. There's a lot of things you can put it in there. Cache is kind of iffy about whether it meets that persistence criteria. How is it updated? Single updates or transactions or distributed transactions? Or care for replacement, which we'll talk more about. Do you use messaging semantics to get asynchronous update of stuff? Can you read your writes consistently? So this is going to be a big deal. I write something and I go to read, do I get it back? Or do I get the old version back? Okay, we'll talk about that. Weekly consistent stores and or caching each make read your writes a challenge. Session state. Session state by definition isn't going to survive a failure, right? But it's the stuff that gets remembered across requests in a session, but not across failures. So session state exists within the endpoints associated with a session. Multiple operation transactions are a form of session state. What do I mean? App A on the left says begin transaction. He talks to app B, maybe the database, across a session, chatters 5 times, and it says commit the transaction. Okay, that's an example of multi-operation transactions. Session state is hard to do when the session smears across the services. In that microservice thing, I can do a request and I go to server 3. I could do another request and the load balancer sends me to server 7. It's hard to have session state when that occurs. Typical state of the art with load balancers is you have affinitization, which means I'll usually send you back to the same microservice instance I did before. But if I don't feel like it, good luck. I'm going somewhere else. So it's hard to do session state when you do that. Data on the inside versus data on the outside redux. Okay, so I wrote this paper in 2005, which says when you unlock stuff, it's different. So data on the inside is inside the database. Data on the outside is not inside the database. Well, what's different about it? Inside, you get classic relational data. It's about values. It's about values within cells, right? It's about holding that still. This is so much a belief of mine that when I was asked to name, I have a column in communications of the ACM about that I can write. There actually wish I would write another couple this year because I haven't done as many. And so the column I picked was called Escaping the Singularity. It's not your grandmother's database anymore. Why? Because to do this relational junk, you have to bring everything to what looks like a single place. And you have to use transactions to make it look like a single time. And when everything is still and everything is here, then relational algebra works. Okay, so that isn't true so much anymore. So you get to data on the outside, where you have messages and files and events and key value pairs and unlocked data not stored in a classic database. And my observation is whenever I push it out of the database, I have to put identity on it. Now, maybe I've got an optional versioning, that's cool, but it's got an identity. And that identity is how I make things work. And I actually have a paper in edit to be coming out soon called Identity by Any Other Name, which talks about all the ways in which identity permeates our environment. Outside data is immutable. Each file, message, key has a unique identifier. It may be a URL or a key or something else. It may be implicit on a session. It may be implicit within the environment, but it has some identity. And then within that, you have immutable data, potentially versions, but each of those is a sequence of different immutable data items. And I have another paper called Immutability Changes Everything from a few years back. So let's talk about the evolution of durable state semantics. So, careful replacement of disk blocks. Back when I was a kid, you had to worry about the following thing. If you went to write a disk block, that disk block had the old value, and then in the middle of the write it had trash, and then in the end of the write it had the new value. And if you had a power failure during that window and you tried to read the block, you could get back neither, there were times when you would get back neither the new nor the old value. And that's kind of annoying. You have to plan for that. You had to think about that. You had to work it, right? And so that was just annoying. So you would do things like, here's file 1, and I've got version 1 at the end there in orange. And then file 1 would be trashed, and then I get version 2. And that was kind of what life was like to update a block. So you could do careful replacement for single block writes with mirrors. What you would do is you'd write the new value into some other place or another parallel file, and only after the new value is safe, you overwrite it. So writing the tail of the log carefully into mirrored disks. Imagine that the tail of the log, the last set of transactions you committed, is in the left half of that block that went from version 1 to version 2. So if that trashed it, you would end up losing stuff you said was to be kept. And that's something you want to avoid. So here you've got two versions. And you write version 2, and then you write version 2, but there is no window in there where at least one of the versions could not be read off of one of the two. Okay? And so that works for mirrored blocks, works for the mirrored tail of the log. That's how I built the tail of the log at the tandem system so as to survive the failures with, well, you're trashing the blocks. And so you could do careful blocks when you have single block writes with non-mirrors. What you would end up doing is you would write version 1, you would write it in a separate block, then once it was in the separate block, then you go write it back to where it was, and then you could continue to reuse that second version 2 of that. And so that technique of being very thoughtful about how and where is an old technique. We don't have to do that anymore with disk blocks because the controllers have got batteries, there's a whole bunch of reasons why we don't have to worry about it. But that concept of carefully putting one foot on the ground and then another foot on the ground and then another foot on the ground to cross the river is an important concept in making the systems work. Careful replacement for record writes. So if I'm going to do a careful replacement of record writes, say I do updates to records in a pre-SQL database. If I was going to do that, that needed careful ordering, setting aside the disk block issue. So I might have to update one record, say record X, before updating record Y. How come? Because if I could see record X, but not Y's change, I could put it back together. But if I saw Y's change and not X's change, it trashed everything. And so I would have to be thoughtful about the ordering of updating records. So here, record 1, and then I can recover after a crash. But in that case where I update record Y first before record X, I can't put it together. And there's an example with this. An example is an application queue. So many of our systems have queuing. You see this in Kafka, and you see this in other things that are being built today. The queue describes, I intend to do this. And then you do it, and then that's cool because you can restart and redrive it, and it's idempotent and restartable. Transactions and careful replacement. I loved transactions. I still love transactions. They bundle and solve careful replacement. So all that stuff with the disks, all that stuff with handling multiple changes out in storage, they deal with it. You just say begin, do a bunch of junk, end, and you're happy, right? Multiple app records can be updated in a single transaction, and it's going to be atomic. The databases make that storage stuff, that storage careful replacement, just not a problem. It's magic. It's taken care of by the plumbing underneath you. Working across time, like workflow, if I'm going to be doing something to get this job done, and then waiting for some other thing to tell me to do the next step, and waiting for another thing to tell me to do the next step, that requires me to be thoughtful about how my data in my application is managed to move from state 1 to maybe an hour later I find out some changes happen, I'm going to do state 2, and that work over time is really challenging, and that's very important with careful transactional replacement. Work over space. If I'm going to work on this computer system, and it's going to talk to that computer system, I'm typically going to have to do the first step here, commit, then send a message. Then it gets there, and I get that second step, do commit and send a message back. Then I come back and I do the third step and commit and do a message that comes back. There is an observation, which is that when you break time or you break space, if you break space, you break time. Let me put it that way. If you break space, you break time. And so that's cool. We just have to get used to it and figure out how to move it forward. Leads us to message semantics. I want to point out this careful replacement. It's déjà vu all over again, as Yogi Berra said. So messaging semantics. Transactional messaging is cool, right? The first transaction includes a desire to send, and then transactional updates happen automatically. So here I am, I'm doing transaction T1, and I'm writing some of my local data, W, X, Y, Z, and I'm going to send a message to that other guy. And then that transaction atomically consumes the incoming message, and that consumption is atomic. So here I am, and I'm going to consume that message, and it's going to change A, B, C, D in transaction T2 on the other system. You can support exactly once messaging with this, okay? A committed desire to send causes one or more sends where I retry until acknowledged. So I'm sending a bunch of things, and then at least once of them gets through. Now, over on the right-hand side, transaction T2, it makes sure that the process is at most once. This is normal, this is cool. If we have relatively static systems, it's really cool. If you have a scalable system with a whole bunch of shards and junk moves around and the identity is challenging, it can be hard because you have to remember the messages you've processed at some level, right? TCP does it with byte stream ordering and sliding window protocol. Somehow you have to do this. It has some relationship. That relationship is a scaling challenge. How do you remember the messages that I'm filtering in for at most once delivery? I got to detect the duplicates. How long do I remember? What if my destination splits? How do I deal with all those issues? Mostly that stuff is nascent and people don't figure it out and it goes wrong when things change. A lot of times. Okay, next concept is kind of fun. Read your rights. Do I read my rights or don't I read my rights? Right. So it used to be back in the day, if you wrote something, you could read it. Go figure, strange concept, right? Linearizable stores offer read your rights. So what does that mean? It means every change to that object or that block or that whatever happens in a linear order. I make a change, then I make another change, then I make another change. And each time I make a change, I can see the stuff that was written before. So linearizable means occasionally delay for a long time when the server is sick, okay? What do I mean by that? Okay. When you, see if I have the, what do I mean by linearizable causes delays? It turns out that it's very hard to have a perfect notion of an order under failures unless I'm working it across multiple systems. And if one of those systems is slow because it's doing garbage collection or just because, right, the whole world doesn't slow down. If you look at the responsiveness of servers, it's usually really, really, really good until it's not. And when it's not, it's not. Okay, it's slow. You can see a typical server go away for a minute just because it's garbage collecting or just because something stuttered. And things like you lost a packet in TCP can cause a while to recover. Okay. So the question becomes, how fast does it happen? But linearizable, meaning if I write something and I see a value, I'm going to see the next value. I'm not going to see something old. I'm not going to see something blue. I'm not going to see something borrowed. I'm going to see that old value. Making sure that happens requires that sometimes things will go slow. And you see that constantly. So if I have a linearizable store, is it going to give me fast, predictable reads? No, because I can't necessarily get to the thing to find the latest value. I may be stalled behind it. And you see this in a lot of stores. Will it give me fast, predictable writes? No. But by golly, if I write something and I go to read it, will I see it? You bet. I will see it. Okay, and that's the linearizable nature of it. Non-linearizable stores do not offer read your writes. Non-linearizable is no guarantee that a write will update all the replicas. It might read an old value. So reading and writing have a very consistent SLA. Why? Because you can skip over sick or dead servers. So that paper I talked about Dynamo from Amazon in 2007, it was OSDI 2007 paper. It's really, really an interesting read. If you are going to write 3 replicas in the Dynamo store, and one of the 3 you're targeting is down or slow or whatever, you just keep going. Write it on another one. If you're going to go read from one of those servers, you go and read and you keep going until you find one. Sometimes you can configure I'm going to read 2 to minimize the chance that I get a stale thing, because you can tell the ordering of them. This is a newer versus older one. And so you will sometimes get the wrong value. Define wrong. You will sometimes get not the recent value, not the latest value read. But by golly, you'll get something fast when you write, and by golly, you'll get something fast when you read. And that write doesn't get lost because it's on 3 servers and it will eventually settle out, but somebody can see the stuff in between sometimes. And so these are trade-offs to talk about. Non-linearizable stores do not offer read your writes. There's no guarantee a write will update all the replicas. You might get an old value. Reading and writing are fast. Skip over sick and dead servers. So a non-linearizable store, fast, predictable read, yes. Fast, predictable write, yes. Read your writes, not promising, pretty much, but once in a while, no. Cached data offers scalable read throughput with great SLAs. Key value pairs are in many computers. They're updated with versions. A read hits one of the computers and returns one of the versions. So if I have a scalable cache, can I get fast, predictable reads? I can get fast, predictable reads, and I can get it for more and more and more reads per second if I add more and more servers. So I can scale the heck out of it, right? Can I have fast, predictable writes? No. It can take a long time for the new version of the thing in the cache to get everywhere. Can I read my writes? No. So there are different stores for different uses. Is it okay to stall on read? Is it okay to stall on write? Is it okay to return a stale version? You can't have everything. And so Peter Bayless has this really great blog post called Linearizability versus Serializability that's really fun. Immutability, a solid rock to stand on. Sometimes we can store immutable things. So if you look for it, many app patterns can create many immutable things. 128-bit UUID is a great example of identity that doesn't collide. If I store immutable things, it can change the behavior of the store. You can't get an old version of something where there's not an old version. There's one version. And if you hit something like Dynamo and it can't find the one and only one version, it says, well, let me try the next server. And so you get an answer pretty fast because it keeps going fast. And when it finds it, it's fast. But it's never wrong because there's only one answer for that key. So that's a huge observation that makes the system behave differently. So if I've got a linearizable store, all of the stuff you've seen, scalable, scalable, scalable. But if I have read your writes for immutable, and I'm storing immutable, I get, yeah, sure, it works. Non-linearizable, though, it works. Scalable cache, it works. So the non-linearizable store to hold immutable data for that purpose has phenomenal characteristics. It's fast to write, it's fast to read, it's fast, and you get the one and only one answer. So the read your writes question kind of stops being an interesting question. So there's interesting options for applications. Non-linearizable stores give fast and predictable writes and reads. And scalable cache gives you lots of fast and predictable reads. Holding immutable data is a huge benefit in designing your app. We don't talk about this enough. We don't teach people about this enough. It makes just a very different behavior out of your system. And I have a paper out there, which is in Communications at ACM, called Immutability Changes Everything, which talks about a lot of these characteristics. Session state, semantics, and transactions. Same process, different process. Back in the day, the database system was a bunch of libraries in your app. Okay, that was the way it started out. Okay, and then you used to run in the same process, and sometimes you'd load multiple apps in it. Then you started peeling it out and putting it into a different process, and you used a connection and a TCP connection to connect them. And the session had session state describing users, transactions, apps being run, current state, Each process in the session has information about it with a session state. And the session state is on each side of the connection from the database to the app that's interacting with the database. Later still, after we pull them into different processes, we start putting them into different processes on different servers. That was actually a pretty straightforward transformation once we had them on different processes on the same server. And session state made that work to split them across a small cluster. And that was really hard, though, in so many ways. I remember doing it. It was a big fight to get it done. So stateful sessions and transactions. Stateful sessions were the natural outcome of shared processes. You knew who you were talking to because you used to be in the same process. You knew who you were talking to so you could remember stuff about the other guy. So you could do transactions and you could chatter within the transaction. I could say begin transaction, here's some stuff, get some answer, here's some stuff, get some answer, here's some stuff, get some answer, commit. And that worked pretty well. Stateful sessions worked well for classic service-oriented architecture. We don't talk enough still about classic service-oriented architecture. I want to write a paper about it. I haven't yet. But it was typically, there was no transaction across that boundary. You had a two-tier environment typically around a classic database, but it was that distrusting boundary. And services are about trust. And that trust, you would just kind of say, forget it. This is my enterprise data. You're not coming in unless I inspect your message and decide I like you and all that kind of stuff, right? So stateful sessions meant the application could do multiple interactions within a transaction. In many circumstances, the rich and complex transactions could occur over n-tier environments and even across multiple back-end databases. So I was chief architect at Microsoft for a thing called Microsoft Transaction Server. Didn't like the name, okay? But it was really how do I build stateful n-tier component-based applications and run them across multiple back-end databases. And we shipped that in 1996. And so you see a client coming in talking to app A, which is talking to app B, which is talking to database 1. And he's got enough session state to manage the transaction there. But even more interesting, the client 2 can come in and talk to app C, which talks to D and E, which talk to 2 different databases. And that meant you had to do distributed transactions across the back end. And there were advantages to this, right? But distributed transactions are sometimes brittle. And so I wrote a paper in 2007 called Life Beyond Distributed Transactions, which talks about the brittleness of that and concerns. Transactions, sessions, and microservices. Microservices stink when it comes to session state. Why? Because you might get load balanced to the next guy, and so you're not talking to the guy you were talking to before. Or he can die. They're not big and heavyweight the way they were, right? Usually they go back to the same microservice instance, but there's no session state because it doesn't always work. Session state is needed to create transactions that span multiple requests. If you can't span multiple requests, you can't do a transaction across multiple requests. It doesn't work that way. That transaction identity needs to be there to do the two-phase commit. So microservices are typically a one-store request. You can read a bunch of junk that's not transactionally consistent. That's okay, right? But if you want to change something, each change is one single change, atomic at a time, right? And so that ends up being not two-phase commit. And so you end up being able to do stuff, but now you're back in the world where that key value store, I'm doing careful replacement. That old careful replacement thing comes back. I'm going to do I'm going to do key X before I do key Y in order to make it all work. Microservices are worth the restrictions, though. Fail fast, load balanced, health media to deploy with canaries, rolling upgrades, fault tolerance, and more. The software engineering advantages and the operational management deployment aspects mean that they're not going away. The app developer is going to deal with not having transactions because this is better to have little pieces of development and things to manage and deployment. So it's just a change that we're in the midst of. It's not your grandmother's transaction anymore. Transactions today with microservices only work on a single call to the store. As the application microservices scale, more instances are made. As microservices compose, they call each other. Scalable stores, fine. Transactions across multiple identities. Distributed transactions across store instances, that's challenging. And you end up with this interesting of scalable linearizability. Per identity, read your writes. Scalable non-linearizability. Per identity, read one or more old versions. When you have a non-linearizable store and you read, what you're saying is I'm going to get any version you've got with a probability stick that is heavy towards the last one. And that's fine if you're using it correctly. We'll talk about usages of that. Identity, immutability, and scale. What's identity? Each identity is represented by some number, some string, some URI, some whatever, right? I don't have a problem with how you do it, which is why that next paper is identity by any other name. It can reference something that's immutable, like New York Times, October 9th, 2017, San Francisco Bay Area edition. That's immutable. It is what it was what it is. It's going to be that forever. That identity can reference something that changes over time. Today's New York Times changes every day. Okay? It actually changes based upon the region of the country you're in. Each version of the identity is immutable. A change makes a new version. That's cool. So you're flipping the pointer from the changeable identity into the unchangeable identity. And every day you flip that pointer to a new immutable identity. But that's separate from the fact that that new immutable identity can always go get the same bits, the same images, the same everything. Okay. Creating an identity for the immutable version is really useful because I can cache, I can copying, I can reference. They're not subject to ambiguity. Where there's ambiguity is the mapping from today to the underlying version, but that's typically much easier to manage when you're just dealing with an identity. So this picture here denotes a linear version history. I go from the top circle to the second circle to the third circle. I have a sequence of things, and each circle is dependent upon the previous circle. The version history might be a DAG. So here I see that I've got multiple parents in some of these pictures sometimes. And so that's a non-linearizable history of things where independent updates happen separately and concurrent versions can come back together representing a fork in history. So cross-identity relationships. Using careful replacement across identities is a tried and true technique. If I find something with identity A and I go from version W to version X, that's great. If I find something from identity B, I can go from version Y to version Z. So here I am in a linearizable world, and I change W to Z, X, and I change Y to Z, and I do them in that order, and then there's no ambiguity. But it's also the case that any and every time I see version Z of identity B, I'm going to see version X of identity A. I never have the case that version Z of identity B exists without that. So the windows of time, where, each window of time where B is VZ also shows A as VX. Careful replacement is predictable over linearizable stores. I will never see version Z of B unless I can read version X of A. That's predictable. Careful replacement over a non-linearizable store will behave really wonky. You may write a version of some idea and read the idea and get the older version. Cache stores will behave unpredictably. So here what I have is I have identity A on the left with 2 replicas and identity B on the right with 2 replicas. So I update identity A to have, and on replica 2 to have, the version W. And then over here I update identity B on replica 1 to have version Z. And that squirts its way over to the other side. So now replica 2 knows version Z. And that squirts from A to replica 2 to replica 1. So version W is over on for identity A. And then he crashes. So now he crashes. So now when I go to read, I see this wonky thing where version Z exists on over on the right, and I don't in that window of time, but I don't yet have W. So it violated my consistency constraints. No matter how you deal with this, if you have non-linearizable stores and you can't read your writes, you can't do any form of careful replacement because it's going to be wonky. There are windows that will be wonky. The only thing you probably also can't do is test it because you won't find those windows very effectively. I think I screwed it up, yes. You're correct. I can't, my reading glasses aren't on, so I can't, yes, I think I screwed it up. I have to fix it. Thank you. Okay, so careful replacement will be buggy over non-linearizable stores. I'm sorry for the confusion. Okay, how append blurs identity. This one is a mind mess. This is fun. Okay, HDFS and other big data system accept writes to append to a big file. So I'm running HDFS. You're right. You're just slapping new messages, new writes onto the end of this big file. That's what HDFS does. And HDFS is designed to have 3 replicas. So you set up a block, and if you write to the first block, then it will take the write and log it locally in its durable store, and then it'll send it to the second replica, who will put it in a block and write it to its store, and then it send it to the third replica, who will write it and put it in its store, and they come back and then they say, that was a delicious write. It was great, I'm happy, and then you write the next thing, okay? And so HDFS deliberately restricts a single writer per file. That's a conscious choice they made. Predictable and repeatable replica data takes careful design. GFS, Google File System, preceded HDFS, and it allowed multiple writers to a file, and it had fixed size blocks as HDFS does. Failures and race conditions sometimes allow different data per replica. What? Huh? So I have multiple writers from 2 different processes hitting the primary. And he's going to take one, he's going to write it. And then he's going to send it to the message to the secondary. But before that message gets there, the primary dies. Okay? And so now the second client says, dude, you're dead. And he goes and he talks to the secondary. And he writes there first. And that write from the first client got to the first replica and didn't get to the second. And there's no protection for that in GFS. And that's documented in a column with Kurt McCusick and trying to remember the name. It was a communications, pardon me, what? Sam Leffler? No, it wasn't Sam, it was Sean. It was Sean Quinlan. And it's in Communications of the ACM. He talks about it in a conversation. It's great, it's fascinating stuff. Now I worked at Microsoft on Cosmos, which is the plumbing under Bing, not Cosmos DB that's being advertised now, but Cosmos, there's 2 different products. And it takes multiple writers. But what it does is, it actually has variable length blocks. They're called extents in that, but they're variable length blocks. You say, how the heck is a variable length block correlated with precise imaging of these replicas under failures? If you do a write from this, and you got multiple writers fighting to get to that primary guy, okay? And the first one gets and he writes it, and then he crashes. And so this master, which is called the CSM, detects that he's gone. And he says to the secondary, how much data do you have in that last block, in that last extent? Oh, you've got, 748 bytes. Great. We're going to take 748 bytes. We're going to make that block be 748 blocks. We'll truncate it. And now you can talk to the secondary and the tertiary, and then we'll keep going. So when that primary comes back up, anything he has for that particular block of the file in excess of the amount that was decided and recorded in the master is discarded. And so now the file is pristine and perfect, even when competing with multiple writers, even with fighting that. So HDFS made a wonderful, legitimate choice. Fixed length blocks, easier to deal with, single writer. Great. That's a fine, legitimate choice. Cosmos made the choice of multiple writers, but we're going to deal with the garbage of variable length blocks, which means every time you want to do a byte array index, you have to scratch your head and look up this stuff and figure it out. So it's just, but the reason I'm raising this is because the notion of consistent append and how do you do that consistently is a very complex area in all of these things. And this is stuff we have to think about as systems builders. So append to file XYZ does not have adequate identity. That's this other interesting thing. Append doesn't have identity. The identity is assigned by the primary. And when you get into failure modes of the primary replica of the data block, the data file, right? How do you manage that? And so assigning the append location means write appends may stall. This whole thing is a big stall, and you're just dealing with the stalls. You want to talk about not having predictable response time? These guys are scratching their heads to go through all sorts of coordination to clean it up. And that's fine. These are batch systems. There's nothing wrong with that. But it's not the thing you want to have your user waiting to do your online shopping for. Okay? That's kind of where I'm going with this. So stalls on big data appends are just fine because they're for batch. So again, I love what's being done. It has huge utility and it's great, but it's different. So let's look at some application example patterns and tie all of this together. Careful replacement over key value. If I have a big, ginormous key value store and I'm going to be doing a workflow and I'm going to be making promises to these other computer systems, I probably don't want wonky, non-linearizable behavior. I probably want it to stall, if it needs to stall, to make sure that I get the right behavior, even if some servers crash and they're scratching their head for a minute or two to figure it out. I mean, you need to realize it typically takes like upwards of a minute for a cluster to decide, that server's dead. By golly, he's dead. I'm not going to talk to him anymore. What do I do when he's gone? You look up and you figure, oh, here's what I do when he's gone. And so if you can't tell he's gone, then you can't figure out how to respond to him being gone. So you can build scalable applications over key value stores, but you probably want linearizable behavior with read your writes. So again, there's this workflow here. And you probably want that to finish in the right time windows. Okay? Transactional blobs by ref. Let's give you an example of something a little different. Say I got a transactional system, but people are doing things like putting out big documents in it. You don't want to put that in your relational system. It's a pain in the tush, right? It's not really good for it, right? So you want to have that big system, and the blobs are correlated with relational data. So you want to put immutable blobs out in that non-linearizable store because it's fast. So the app says I want to run a transaction, then I'm going to write these three things out, and then I want to do another transaction to say they're there. Okay. Now, the database itself will sometimes stall, although they get a lot of engineering to avoid the stalls. They don't very often. But the non-linearizable store will add to it, won't add to it because of the non-linearizable behavior. But I'm putting immutable stuff, so it's going to be crisp and transactionally good. So the blob store can be implemented with many commodity servers. You don't want to delay. Humans are waiting for it. And the non-linearizable store has excellent SLAs. Okay, so that's why read your writes is immutable in this picture. This one's fun. E-commerce shopping cart. Each shopping cart is for a separate customer. Nobody's excited about transactions across carts. Nobody wants that, right? To heck with that. And there's customers are very unhappy if the shopping cart stalls. There's measured data, tons of measured data from many different e-commerce sites. If you stall when people are looking at their shopping cart, they leave. They just go clean the kitchen, right? They don't stay, right? If you give them the wrong value in the cart, because it's an old value of the cart, then they fix it and they stay. And so it's big, big, big business difference. You want to have that shopping cart, even if it's wrong, to be presented there. And you can do additions and subtractions to the shopping cart in a way which settles out. They're eventually consistent. If you do the multiple things, you can fix it up. Shopping carts must be right now, even if they're not right. So that whole tension, do you want it right or do you want it right now? We don't talk enough about it, right? That's a huge issue. It's measurably better for the business to show the wrong result promptly. Measurably better. Measurably happier customers, measurably better, right? And so users are asked to verify the cart before completing. In a non-linearizable store, sometimes old versions of the cart exist in the version history directed acyclic graph. Items are added and deleted. Relatively simple cart semantics can clean the mess up if there's divergent versions. So you have low latency predictable reads, low latency predictable writes. Yes, read your writes. No, I'll give you the wrong answer, but I'll be at you real fast, and it's all good. E-commerce product catalog. Feeds and crawls processed by the backend. So you see literally millions of people selling stuff and tens and hundreds of millions of products on some of these big e-commerce sites. They feed things in describing the products. There's people crawling the web to go to manufacturers' sites to go and pull stuff out to get the descriptions of the vacuum cleaner that's going to be sold and formatting it in a consistent way to fit into the e-commerce website. So data from webs and from partners produces distilled product descriptions. Each product has a unique identifier. The identifier takes you to a partition. The partition takes you to a replica via load balancing. The replica and that code for the product unique identifier takes you to the product description. If you need more products, you make more shards horizontally. If you need more read traffic, you stack more vertically. Okay? So backend processing and pub/sub are throughput sensitive. For the most part, it doesn't matter if it takes 1 second or an hour to get the product description updated. It matters that the aggregate amount of junk you're processing can get stuffed out into those caches. Right? Latency is not important. Different replicas may be updated async. User catalog lookup is latency sensitive. Scale is important. It's okay to get a stale version of the product. So what do I have here? I have low latency predictable reads, yes. Low latency writes, Read your writes, These are just an example of where I don't care about that. I don't care if I get the old description of the vacuum cleaner on one read and then the new description on the next read. It's like, okay, the world didn't end. And so that's got a lot to do with the semantic of the identity of the vacuum cleaner in the description. I'm not doing joins across it the way I am in the generalized relational database. It's a different critter. So lots of scale. Search. Web crawlers feed search indexers. Very similar to the product catalog. I'm crawling the web, I do the search indexing, I'm sharding it, I'm putting these into n-grams that I'm searching, and I push them out of the indices so the search requests can come. Updates to the index are not super latency sensitive. It's not 100% true. The high-end search things like Google and Bing and so forth have parallel high-speed response things for latest news-breaking things if there's been a big event that's happened in the world. But for the most part, everything is happening kind of in the slow boat, right? Getting it there. Very important that search requests get low latency. Retries to other servers in a shard are okay as long as the latency is bounded. So in search, instead of hitting one of those shards, I have to hit all of them and then aggregate it. And so if one of those calls is slow, I'm in trouble, right? It slows me down a lot. There's, to me, one of the handful of best papers to have a systems person read, a systems student read, is Tail at Scale by Jeff Dean and Luis Barroso in Communications of the ACM. It's amazing, right? The broad idea is if you call one of those shards and one of those servers, if you call that and it takes too darn long, okay, then what you do is you say, if it's more than 95th percentile, like 19 out of 20 requests is faster than this one's taking, I'm going to say, to heck with it, and I retry to another replica in the same shard so I can get an answer from all the shards. Now, the 99.9 percentile answer is dramatically lower, and there's just amazingly cool descriptions that happen, and that paper is just essential for any systems, computer science person. So, low latency predictable reads, yeah. Low latency predictable writes, not in general. Read your writes, nope. This is all jittery and flaky and crazy. Lots of scale. Big data appending to big files. Okay, so HDFS and Hadoop have big data. Each byte offset is assigned a form of linearizability of the append. So the question is, who's giving the semantics? The appends will usually be very fast but be delayed. Appends can be delayed while the system copes with sickness or death. A read of big data can bound the SLA. And so the issue is writes don't matter a lot in a batch system. And the reads can retry to another replica. And so in this system, because it's batch, you care much more about aggregate throughput. If 1 out of 100 requests is slow, that's fine if the other 99 are fast enough to make up for it, which is different than when there's a human being waiting for the answer. And so it's different than where I need all of the shards of the search index because I have to have all of them come back together and I need to get that human interaction SLA. Conclusion. Conclusion is it's about the application pattern. Low latency reads, writes, read your writes. Careful replacement has to work across multiple key values. I need to read my writes. I will take the stalls because I'll get a mess if I'm doing something like a workflow. I'll get a mess if I get a stale answer. Blobs by ref, because they're immutable, I can have non-linearizable and immutable, and it's like phenomenal, right? There are other examples of that immutable that are phenomenal. E-commerce shopping cart, it's actually okay to give the wrong answer, and so I just need it fast. Product catalog, the same thing. I want my reads fast from the product catalog. Search, I want my reads fast. That's the thing that matters. Append to big files. I can get my reads fast. I'm not that worried about the writes. The data is immutable. And so I think there's interesting work that we can do with this area. It's actually the order of the write that is the fulcrum of the indecision. So I wrote a paper called Standing on the Distributed Shoulders of Giants, which is poking fun at physicists. And one of them is Heisenberg was on the right track, one of the sections, W-R-I-T-E. And the point is you can know where you write, or you can know when you write, but you can't know both. In order to solve that, the identity of the order needs to be assigned at the client that's writing. And so, which is all tangled up in this stuff. So linearizability and read-your-writes are not always required in modern scalable apps. How you use your state depends on your app requirements. So I always tell everybody, including students, especially students, when you're doing a presentation, you start with the takeaways. And it takes me 1 to 2 hours to write a typical takeaway slide. Just one stinking slide. And I'm always revisiting it. I'm always going over it, blah, blah, blah. So this is what I hope you remember. This is what I started out to write, okay? State means different things. Session state. Stateful sessions remember stuff. Stateless doesn't remember on the session. Durable stuff. Stuff is remembered when you come back later, even after failures. Most scalable computing comprises microservices with stateless interfaces. They're great. They have partitioning failures, rolling upgrades, stateful sessions are problematic. Microservices may call other microservices to read data and get stuff done, but the composition of this is kind of hard, right? And figuring out how to make it predictable. Transactions across stateless calls usually aren't supported in microservice solutions. Microservices means no server-side session state, which means no transactions across calls, which means no transactions across objects. There you go. So this is what you're getting as part of the package deal with microservices. Coordinated changes use the careful replacement technique. It's the same technique from computing early days. We see it all over the stack. It's, déjà vu all over again. Each update provides new versions of the stuff with a single identity. Complex content within the new version may include many things, including outgoing and incoming messages. That complex content of app-defined messages intending to be sent is very powerful, very powerful. Different applications demand different behavior from durable state. Do you want it right? For example, read your writes. Or do you want it right now with bounded and fast SLAs? That's, to me, just a big deal, right? Humans usually prefer right now to write. Sometimes they care to stall to get the right answer, the correct answer, but usually they just want right now, even if it's not perfect. Many app solutions are based upon object identity, may be tolerant of stale versions, and immutable objects can provide the best of both worlds by being right and right now. So that's it. I got some time. Thank you.
Explain to me more about right now versus right, why humans are that way.
Because you get impatient. Humans are impatient. So the question is, why is right now better for humans?
How wrong can it be? People are okay with it.
That's not something I can tell you. I mean, I'm telling you that as an app designer, as a builder of a system, you have to think that through and try to empathize with what your humans are going to do. Mostly, though, most cases I can work around to finding a right now answer that people are pretty happy with. It's kind of crazy. But it works that way.
Yeah. It sounds like the right now. If you're uncertain, you ask again. Right now, and if it's consistent, then.
Well, people repeat. They ask again.
Yeah.
They do. They repeat and they ask again. But it's
flaky, basically. You repeat.
I mean, what do you do if you get the wrong? If you look at your shopping cart and it's not right? What do you do? You fix it. Well, a lot of times when you go to buy, you do. When you go to push the thing and you review it and then you say, wait, what happened? I added that thing. Okay, I'll add it again.
You delete something and add it again, or
Sure. It's what people do. But if this thing just locks up and says no, I'm spinning, the little wheel, then you go do the dishes.
Were you at Tandem when they switched to the instead of doing the banks and the secure stuff, but going to the 100,000 gamers on simultaneously?
No, not so much that. No, I'd left in 1990. Okay. Tandem was an interesting box, though. Yeah.
That was an interesting variation of the problem.
Yes. Did this kind of hang together? Did it make sense?
Yeah. Are there terms for the various? You had a chart with yeses and nos in various columns. Are there buzzword terms for various combinations?
Not that I know of. This is me making this stuff up.
Well, actually, I'm surprised. That was the version of my question. I'm surprised you haven't adopted the database convention of the acronym ACID.
Well, first of all, I love ACID. I mean, and I haven't talked to the guy who invented it since the weekend. And so Andres is an old friend of mine. and I've been doing ACID
You
stuff.
should explain what ACID.
ACID stands for atomic, consistent, isolated, and durable. And it is the description, and consistent's a little weak, but most of those terms are very strong. And it describes how does the transaction talk about the sequence of transactional behavior, which basically the goal is to make it look like nothing else is happening when you're doing your work in a single transaction. Everything else happens before or after. And that is the technical concept for that is called serializability, as in I could create a serial order. Doesn't mean it is serial, it means it could be serial. And so I just am writing down observations. This is, to me, I just think about random junk and try to write it down, and I realize that this is not completely well-formed, but I have a day job building systems, and this is recreation. It is honestly just stuff I do on the side. Well, thank you. It's just.
So over the weekend, there were reports that some of the big medical, wonderful computer systems can't handle daylight savings time changes. What did Tandem do for time internally?
I don't recall
Tandem
all
at
of
the
that.
same time, and he says that banks, that hospitals put Tandem machines in the billing department and had no place near patient.
That wasn't typically patient data.
Yeah.
You're correct. It was billing stuff that was running in hospitals.
Which, yes.
Well, as far as I could tell, the problem was that somehow they were using, local time instead of UTC.
It's entirely believable. Every system has some stuff that goes wrong. And
Well, you would
could
think that they would have, they've been around for more than a year. You would have think that they would have fixed it by now.
I don't know the details of something that happened 40 years ago with that. I don't know, 30 years ago. I mean, I honestly don't remember that one.
Well, they're all built in Russia, where there's one time zone. And it doesn't change.
So any other comments or thoughts? Yes?
I actually have a question. My takeaway from the presentation is basically there are different application-specific characteristics for storage for different applications. But does that advocate for building different file systems with different characteristics based on the application? So there's no generic storage of file systems anymore, rather than we should first look at the application and build a stack from there.
I think we're still, so the question is, does it advocate for having a single storage that can do all of this stuff? And my instinct right now is no. That doesn't mean over time as an industry we don't learn. I think better discussions about the trade-offs are what I would want to start with, if you understand what I'm saying with that. And I haven't seen single solutions that are a panacea. I think you could build some of these semantics for these single solution, on top of it, a single infrastructure if you wanted that maybe gave you backup and DR and some disaster recovery, but I don't know, I haven't thought about it enough. On a whole, where I think the issue is that's very complicated is people are rushing to microservices for good reason. And mostly they don't know what they're getting into. That's just to me, that's the more important thing. And so they'll pick a store that doesn't work for that, and they'll have expectations for how their app's going to compose without thinking about that. Transactions and databases have been so successful that we've kind of lost the skill set to deal with the funky behavior of random systems because it coddled the app developer. And so the challenge is when and where and how do we have higher level abstractions that still coddle the app developer. I'm a believer in that, by the way. I'm a big believer in platforms. When I was young, it was the TP monitor. And that was, how do I manage 400 terminals when they have to run through one process, and the guy who wants to work, guy or gal who wants to program for an insurance company doesn't want to think about asynchronous management of the messages from the terminals. And so that was phenomenal. Right. Now we're trying to do this at cloud scale. This is why I targeted Salesforce. It's a fascinating company with a great bunch of good stuff, but it's about making it easy for people to build their solutions in the cloud. Nobody else does that in the cloud. Now, the ways in which that works in combining databases and combining the microservices and growing solutions that way, I don't think we have a really good guidance for everyone yet. Did that make sense? And it's going to be fun. Hey, I've been doing this for 40 years. It's been a great ride. I'm looking forward to doing it for a lot more years. It's just a hoot. So, yes. I'm sorry, just one sec. Go ahead.
So my question was kind of along the same lines of what you were just saying, that, what this shows is there's still trade-offs you need to pay attention to. There are still, different designs that are appropriate for different application use cases. But what's changed, thinking about your digression about Tandem at the beginning, as you said, it used to be that you had a whole team of specialists to develop a system, an application, whatever it is. That's been much more democratized in the sense that now anybody can go and throw together a microservice-based application, probably not knowing about some of these trade-offs, and they may not even have a computer science background.
So yes, but the pressure point that I was speaking about with Tandem happened in the 90s, okay, where it was just Unix, and you can just go down the street and buy something that did your needs, met your needs, and ran on Unix. You installed it without hiring programmers. But then that changed over time under scale and distribution and mobile devices, and the list goes on. And so that's grown. The complexity of the standardly accepted app has grown. Am I making sense?
Right, no, that's true. Right, but I guess my point was it's much more possible now for someone with far less training, understanding of these trade-offs and so forth, to build an app that where now, I think it comes back to what you were just saying, that then you can't expect that the designer of this system is necessarily going to have the background to be able to take all of these issues into consideration.
So the thing I mentioned about a platform, I love platforms, right? The platforms happened, like transaction, TP monitor platforms and cloud-based platforms and IaaS and so forth, have happened because someone looks around and people are solving junk in ways that are one-off. And then they're saying, oh, this is a pattern for how people are building their application, but they're doing it this way versus this way. And they say, wait, I'm going to make it this so that there's this interface, this abstraction, this platform, and if you will, platform as a service, right? That does these things, and they don't have to think about a lot of stuff, right? Salesforce does just a phenomenal job of masking multi-tenancy. So we're sharing very expensive resources across many, many, many concurrent tenants and making it so that the customers don't have to worry about that. And that's a phenomenal platform as a service. But as the applications grow, as big data grows, as data science grows, as all these new cool things go, I look forward to seeing how those are made more approachable to folks who don't have PhDs in computer science. That, to me, is the fun. That's the real fun. Did I answer your question?
Yeah, I think so.
Okay. Did you want to try again?
What's going to be the exciting thing for tomorrow?
Tomorrow?
Yeah.
I'm just going to go back to work on the thing I'm building. I'm not going to tell you about it.
Sorry, non-disclosure.
Sorry.
Is there a number for efficiency or something? If I took a simple server and just had no replications or nothing because my problem will fit on a simple server, what's the sort of resource cost in doing it in,
I don't care.
No, I don't care either.
No, the reason I don't care is because the opportunity cost is much higher.
Pardon?
The opportunity value is much
but
higher.
I was just curious.
And there's no one answer to that. I mean, when I was at Tandem, in the early days, we were neurotically checkpointing every write across computers. And they were doing, you get a computer and the guy who was doing the data would send a checkpoint to the other, say, yes, now you can do that right. It was fine. And then we started using log-based techniques to do it once, and then it would asynchronously go over, and it was much faster. And then we had to change the transaction semantics so that if he blew, then it would clean it up. And all of that was a great improvement because it didn't modify what the programmer saw. The programmer saw a transparent behavior out of the app, but we made less work happen. These things are going to happen at so many different areas. So I don't have a way to answer your question without us getting into a far more detailed discussion of what the work is. Do you understand? But in general, you make it slow and then you make it fast. I mean, one of my cynical comments is that when you're releasing software, there's two kinds of releases. There's performance releases and there's anti-performance releases. And you make this new feature and it goes slower, and then you make it go faster. That happens a lot. So it's just, A lot of these new things are, how do I lower the barrier to entry for the developer? That's kind of the key point at this point.
When you say slower but more reliable, hopefully.
Well, but slower and more functional, and
That's fine.
right. There's a bunch of reasons you do it, and there's a bunch of reasons that happen, and then once the performance is improved, the aggregate performance is usually way the heck better because you worked at it, and a few things are a little slower here and there, and it's just natural. That's the way things work, right?
Besides, if you release it and it's slow and nobody cares, then you don't ever have to make it fast.
Understand?
Well, shall we take him to dinner?
Yeah, let's-
Sounds fine.
See how many of these people?
How many
Thank you,
people
guys.
go to dinner today?
Well, we should.
Thank you.